Good morning. Welcome to the class of Discrete Math. So today we'll have a lecture with the slides by request of the people on Zoom who had problems with viewing the blackboard or the whiteboard if you wish. So the topic for today will be P and NP. I will now share the screen and we'll start the lecture. So let me see. Okay. Okay, so I will now open the brand new slides and we shall discuss the topics connected to Cook-Levin theorem and well, starting of course with the definition of the NP class. Share that. I'll make it a bit bigger here. So I hope that the people on Zoom are seeing. So please tell me whether you see the slides. Somewhere in the chat, I don't know, somewhere else. Okay. Well, chat. Yeah, so you see the slides. So the people in the auditorium are seeing them on the big screen. And what we're going to start with is, well, the good old polynomial class. So when discussed now, well, till the very end of this lecture, we discuss only decision problems. So this means that these are algorithmic questions with yes, no answer. So we had good examples like, I don't know, whether a formula is satisfiable or whether a formula is tautology or whether a graph has a Hamiltonian cycle or, for example, whether a graph is bipartite, that it includes two parts, two halves, and all the edges are only between them and stuff like that. So this is the input data is something, well, some finite object in general, and the output is only one bit, yes or no, or we will also say it as 1 and 0, just as in Boolean logic. So for convenience, we suppose that the input data is a word of an alphabet. So this is a string of symbols. We can actually suppose that this alphabet is also of zeros and ones. So we have a bunch of zeros and ones as the input, and we have only one bit as an output. So of course, if you have a bigger alphabet, don't know, like the English one, you can always recode it as a binary one, just using byte strings for letters. So the size of the input, what is denoted by x, is the length of x in symbols. So the number of symbols in x. And the decision problem is in P class if there exists an algorithm for solving it whose worst case running time is bounded by a polynomial depending on x. Just for 1 second, I will reshare the screen. Okay, and it should look better. So what does it mean, the worst case complexity? Worst case means that among all x's of the given length, we compute the time which the algorithm takes to solve the problem. So this time should always be finite. So on no input, the algorithm should run into infinite loops. Otherwise, it actually does not solve the problem, not even in polynomial time, but in any time. So we'll get a bunch of numbers for every x of given length. And now we take the maximum. So we take the maximal complexity for given length of the input. And this is the complexity for the given length of the input. And this should be bounded by a polynomial of the size of the input. So this is asymptotical behavior style complexity estimations, because we're of course interested in what happens when x is very big. Because for small x's, we can just make this polynomial say a constant. We have a big constant. For small x's, it suffices. But when the x starts growing, we can see the growth of the worst case complexity. And it could be either polynomial or super polynomial. For example, if we try to do some brute force, like find all the solutions of I don't know, to try to guess the satisfying assignment just by brute force, it will go exponentially. And it's not bounded by any polynomial, so this is hard. So the P class is the class of problems which we consider in a sense tractable. So in a sense solvable in good, reasonable time. So of course, this is a rough approximation. People could argue that if the polynomial has a very large degree, I don't know, like 100, then it's of course not practically implementable. But if it is not polynomial, then usually it's not good for implementation. The only situations where you can really implement non-polynomial algorithms happen when the worst case complexity is really not the complexity measure you want to use. Sometimes, so the classical example is the simplex method in linear programming. So solving linear inequations and optimizing linear functions. So there is the well-known method called simplex method, which is worst case time exponential, but used in practice just because these worst cases never happen. Or sometimes there's really some hidden parameter inside the length, which is really small, and this gives us the exponent or something like that. But in general, polynomial corresponds to something well computable, and exponential corresponds to something which, well, is a question. So this is the P class. Now the NP class. So there are several equivalent definitions of the NP class. We will discuss two of them today. So the first one comes from the notion of what is NP, how it is pronounced, is non-deterministically polynomial. So this refers to the notion of non-deterministic computations. So the notion of non-deterministic computation can be discussed for any sort of computational model. You can try to find out that there could be a non-deterministic computer, which makes non-deterministic choices. We will do it on the material of Turing machines, as we discussed last time. So our basic model of computation is Turing machine. It is important for proving one theorem today. So we'll stick to Turing machines. As we discussed last time, the polynomiality for Turing machines and polynomiality for other computational models is equivalent. The degree of the polynomial could be different, but the polynomiality itself is the same. So the Turing machine can branch. A deterministic Turing machine cannot have such pair of instructions, or it's different, say Q1, Q2, or B1, B2, or D1, D2. So remember that I will remind you that P is the state and K is the letter which is observed by the head of the Turing machine. So we're now in the situation where we know that we're in state P, we observe A. Usually, this information is sufficient for us to make the right next step. Or sometimes it can say fail, that there is no possible instruction to do. This is the situation with deterministic machines, which really model real computers. All real computational devices are deterministic. They know what to do at each time. Sometimes they can toss a coin or do something like that, but they do something. So here we have two instructions in the same situation. So the machine can either go to state Q1 and write down B1 and make the movement D1, so it's right, left, or no move. Or it can do the following. It can do Q2, B2, D2. So, and there is no hint, no clue for the machine what to do. So it is in the situation of non-deterministic branching. So the question is, how does this machine compute something? So there could be several possible definitions, and what is implemented in the definition of the NP class is what is called angelic choice, angelic from angel. So when we come into the non-deterministic branching place, we should make a choice, and we wish the answer to be yes. So we are positive, we want the answer to be yes. And then we suppose that there is an angel who gives us a hint at that point and says that you should go this way, and then you will win. So this boils out into the following definition, that if at least a non-deterministic Turing machine can have many execution trajectories, many execution tracks. So if a deterministic machine has only one execution track, this can have many. And if at least one of them wins, if at least one of them yields the answer yes, then the total answer is yes. And the answer no happens only if we fail in all possible ways of execution. So of course there is dual notion, which you could call mnemonic choice, when you can win only if you win always. If you have an opportunity to fail, you will fail. And this dual notion yields the class of co-NP, which is the dual for NP, of course. So if you take a language or a set of a problem in NP, and if you invert it, so you just flip yes and no, you'll get a co-NP problem. So for example, the problem of satisfiability is NP, because you can implement non-deterministic guess. So how can you solve, for example, 3CNF or Hamiltonian cycle or just SAT in NP? Well, you start with just branching, and guessing the answer. And then when you finish with guessing, you just check whether it is the correct one. The check itself is performed in polynomial type. So you're given a satisfying assignment, or well, no, an assignment which you're supposed to be satisfying. And then you just substitute the zeros and ones into your formula, and you get the answer, yes or no. And the assignment is just non-deterministically guessed. And since we have angelic choice, we suppose that the angel gave us the correct assignment, which yields us the answer yes. In the dual problem of tautology, if we check the formula for being a tautology, we're in a situation of demonic choice. So again, we try to guess a satisfying assignment, but this assignment is now given to us by the demon. And the demon wants to win against us, and therefore they will give us the assignment which is bad. And if there exists an assignment which will yield no, the demon will give us this assignment. And therefore the answer yes is only in the case when all assignments are satisfied. So this is the situation of tautology, which is co-NP. So these classes are dual. Basically, the whole theory for NP also can be dually rewritten for co-NP. As we discussed in the beginning of the course, there is the problem of satisfiability, the dual problem of tautology, and you can flip between them. But we're now discussing the NP class. So, and what we should also understand here, that the NP class, unlike the P class, is asymmetric. So if we flip the result, if we take the complement, so for yes, we will answer no, and for no, we'll answer yes. Then the problem, if it was in NP, it will become a problem in co-NP. So it will come to the dual class. While P is symmetric, so if you have a P problem, then you can just deterministically solve it and then just swap the answers. This is possible. So this is one definition of the NP class, which is sometimes quite convenient, but there is also another one, which reflects the idea of choice more, or of hint by the angel more consistently. So this is by the hints, and let us denote our decision problem as A of x. So this problem which computes a function which takes an x and returns 0 and 1. So it's a function from the set of words into zeros and ones. And we suppose that it is of the following form, that we answer 1 if and only if there exists a y such that first y should be of polynomial size. And second, there should be a polynomially decidable R in P, a polynomially decidable relation, so a polynomially decidable function of two arguments, x and y, and this should yield 1. So how is it realized in, so y is the hint. And the example of y is, for example, satisfying assignment. So we cannot solve, we don't know how to solve SAT in polynomial time, but if someone gives us a hint, the satisfying assignment, we can do this, yeah? If we know the satisfying assignment, we check it in polynomial time. Again, if we have a Hamiltonian cycle, if we don't know the cycle, the Hamiltonian cycle problem is supposed to be hard. We don't know how to solve it. But if we have the cycle given as a hint, then we can solve it. And the hint should be of polynomial size. This is important because otherwise we could get too much information. So Q is some sort of polynomial. It may be not the same polynomial as the polynomial bound for R, but maybe. So equivalence of definitions is proved as follows. So from 2 to 1. So if we can do non-deterministic computations, we don't need any hint because we can just guess it. Just non-deterministically guess it. And this was the correct hint. And recall that here you will have the existential quantifier. The hint should exist in order to win. Again, in the co-NP class, here you will have the universal quantifier. From 1 to 2, it's a bit hard to prove, but also quite easy. So suppose we have a non-deterministic algorithm. How can it be rewritten as a deterministic one with a hint? So actually, so here is this non-deterministic algorithm. It's all its execution paths. And suppose that each branching is binary. So we have only two options for non-determinism. This can be achieved just by taking, if you have a, say, triple non-deterministic branching, you can split it into two binary ones. So at each time when we branch, well, we either branch to the top or to the bottom. It's just on the picture. So actually we have two choices. And let top be 1 and 0 be bottom. So if we choose to go up, we make it to the top. We write 1. And we go down, we make choice 0. And now, well, the number of branching points at any path is polynomially bounded because our computation is polynomial. Our non-deterministic algorithms should make only polynomial number of steps. Otherwise, we are not in NP class. And let us write down the number of the choices we made. So here is going to be 0, 1, 0, 0. And this is going to be our hint. So we put our hint as the sequence of choices we made. And we can suppose that then this hint was given before the start of our computation. And that's it. So instead of doing the choices inside the execution, we can just ask for a word of hints before. And this word is going to be a polynomial one, and we'll just take the answers from this word. So we do not ask the angel to help us along the computation. Instead, we just ask for help in the beginning. And this is the equivalent thing. So there are two definitions of the NP class. And now the theory of NP-completeness. This is the central part of the course in complexity theory, mini course. So trivially, P is a subset of NP. Well, in both definitions, this is obvious because if you have non-deterministic computations, you can just refuse to use non-determinism, you can make it deterministic. If you speak in terms of hints, again, you can just take a hint of 0 length. You can refuse to request help from external forces. You can just do everything by yourself. So if you can solve something polynomially, this is an NP. And nobody knows, well, that this inclusion is strict. So whether P is equal to NP or not. So for example, nobody knows whether 3-sat can be actually solved in polynomial time. So this is the great P equals NP problem, $1 million prizes for that and stuff like that. So what should we do? So basically, most computer scientists don't believe that P equals NP. They rather believe that P is not equal to NP. But no proof is known. So instead of, well, of course, people are trying to prove this, but they are not successful in that. As an substitute, as an ersatz for this, the theory of NP-completeness was invented by Cook, Levin, Karp, and the people in the middle of the 20th century. And informally, NP-complete problems are the hardest possible problems in NP. So we have the class of NP. And inside this class, we are trying to find out what are the hardest problems. We will formally define this in a minute, but one corollary that in particular, if you have a polynomial time solvable NP-complete problem, then this would yield that P equals NP, because the hardest one. So if this is polynomial, all others are indeed polynomial. And contraposition says that if P is not equal to NP, in which we believe it's highly likely, then any NP-complete problem is not in P. So we get conditional complexity results. If we believe in this, as they call it, complexity conjecture, that P is not equal to NP, then we immediately get non-polynomiality for a specific problem. Not just that we have, so this is an existential claim. What does it mean that P is not equal to NP? This means that there exists some problem which is hard, which is NP but not P. But if we know that a particular problem is NP-complete, then this would yield non-polynomiality or high complexity for a particular concrete problem. So this is a concrete, so the theorem of NP-completeness is the concretization of the P not equal to NP claim. So we start from the conjecture that P is not equal to NP, and we yield the result that a concrete particular problem is not polynomially solved. So this is how this theory works. But it's all conditional results. So if it happens that P equals to NP, all this theory becomes void. Well, it's formally formally valid, but in this case, all the problems will be at the same time polynomial and NP hard, which is just trivialization of the situation. But people believe that P is not equal to NP. Of course, if we try to make this as a basis, I don't know, for cryptography, this is a bit vulnerable, that we are based on a non-proved conjecture. But it's the usual case in complexity theory. You will find it everywhere. So how do we define NP? So we give a big slide here. First, we define the notion of M reduction or Karp reduction. And we say that a problem A can be reduced to problem B. And it's written like that, that A is less or equal than B. So P is for polynomial, M is for M reduction. It's multi to 1 or Karp. It's not, so remember, M is here not a natural parameter, it's just a letter. So if there exists a polynomial time computable function, f, which does the reduction. So A of x equals 1 if and only if B of f of x equals 1. And the idea of reduction is as follows. So suppose we know how to solve B quickly. Then we can solve A. Just as follows. So how to solve A? We just compute this function f and submit it to B. And now B does the job. So this means that A is at least not harder than B. So there's only a polynomial gap between them. So this reduction can be used for proving polynomiality of something. Yep. If you know a polynomial algorithm for B and you know a reduction, then you know a polynomial algorithm for A just by this equivalence in the box. But we're going to use it backwards in a sense. So yeah, before going further, I would say that this is Karp reduction. There are also other versions of reduction. This is quite a limited one because here we can use the algorithm for B only once. So if we want to solve A, we take its input, we make some preparation, we transform x into f of x, and then we should run B one time. There is a more elaborate notion of Turing reduction or multi-reduction where you use B as an oracle. So you can start B any polynomial number of times. This is a more, say, general version of reduction, but for NP-completeness, they have chosen this Karp version. So it's a restricted one. And now we put the definition that the problem B is NP hard if any problem, oh, sorry, this should be NP. This should be NP, not P. If any problem of NP is easier than B. So NP hard problems are on top of the NP class. So any NP problem can be reduced to this problem, to this NP hard problem. But these NP hard problems could be themselves not in NP. Well, they could be even undecidable. We don't know anything about B. So the problem is called NP complete. If it is simultaneously also, there should be NP here, sorry for that. And it's NP hard. I will fix this in the slides on the webpage. So it should be an NP itself, and it should be NP hard. So these problems are NP complete. And this is the complexity picture. So we have, it is under the conjecture is conditional if P is not equal to NP. If P equals to NP, everything gets trivialized. So we have this NP class. The easiest problem in the NP class are polynomial. They're all, of course, polynomially reducible to each of them just because, well, you don't need any reduction if you just can solve your problem just polynomially. And these are NP hard problems. These are problems which are harder than any, well, harder or equal to any problems inside the NP class. And it happens that these classes intersect, and there are problems which are simultaneously in NP and NP hard. And we'll just prove this by example. And these are NP complete problems which form the top of the NP class, the most complex problems there. And if we prove that something is NP complete, then we know that this is hard and probably not solvable in polytime. So we prove this by, usually this is, yeah. Yeah, so proving that the problem is NP complete gives an evidence that this is hard. So if P not equal to NP, it's not polynomial solvable. The usual method of proving NP hardness is by backwards reduction. So suppose we know a problem A which is already NP hard. And in order to prove NP hardness of a problem B, we have to reduce the old problem A to B. So this is opposite to the thing we usually do. So usually if we want to prove that something is easy, we reduce it to something which we know to be easy. Yeah. So we can reduce, I don't know, finding I don't know, some construction in a graph to 2sat. We will see this in the end of the course. Say 2 coloring of the graph can reduce to 2sat quite easily. You can just write down the coloring conditions as a Boolean formula. And this reduction, we know that 2sat is polynomially solvable, then 2 color is polynomially solvable. But here you have to use the backwards reduction. So we suppose that the problem is hard. And if we reduce that problem to our problem, what we'll see? We'll see that A is easier than B. But A itself is hard, therefore B is even harder. And this will make B also NP hard, formally speaking, by transitivity of reduction. So you reduce B to A. You reduce A to B. But then any NP problem C can be reduced to A. And then C is reduced to A is reduced to B, which means that C is reduced to B. So by this reduction and by transitivity, which is actually composition of reductions. So you reduce C to A, then A to B, and if you take the composition, you will reduce C to C to B, sorry. So this will give us NP hardness of the problem B. So again, the thing you should understand from this room, just remember, otherwise you will always get confused with that. That if you prove that something is easy, you have to reduce forwardly. So you reduce something which you want to prove to something which you already know. If you prove hardness, you reduce backwardly. You take the problem which is known to be hard and reduce it to our new problem, which we prove to be hard. So this is the standard method of proving NP hardness of anything. To prove NP completeness, you have also to show that it is inside NP class, which you have to do. But how do we bootstrap? So in this proof of backwards reduction, we had to use a problem which is already known to be NP hard and produce new NP hard problem. But how do we show it for the first one? And this is the Cook-Levin theorem. So Cook and Levin, well, actually it's the usual Soviet American situation when two people in different parts of the world in different groups of countries did the same, basically at the same time. So Cook in the USA and Levin, at that time he was in the Soviet Union. They proved this big theorem that SAT is NP complete. So again, we know that it is NP. So we have to prove that it is NP hard. And since we don't have any NP, and if we so we know this is NP and we have to show that it's NP hard. We don't have the opportunity to prove this by backwards reduction because we don't have any NP hard problems at hand right now. We have to prove it directly. So we give only a proof sketch. So we suppose that there is an NP problem, so there's no typo here, fortunately, and we just show that it's reducible to SAT. For any arbitrary NP problem, this is just the direct way of proving. We give only a proof sketch, so technical details can be restored, but just how the proof works. So A is solvable by a non-deterministic Turing machine. We use definition 1. And we encode each configuration of the Turing machine as a binary word. So a configuration, so M here is the number of bits. So we encode each symbol as a byte of a corresponding length, where the length is the logarithm of, roughly speaking, the logarithm of the number of symbols in the alphabet. And Q also is encoded as a symbol. And here, just for convenience, we do the following. So this is letter AI, which is observed. Before this letter, we write the byte which corresponds to Q. This is M bits, M zeros and ones. And before each other symbol, we just write the padding of zeros. So the code of Q is not just all zeros, and this is just the padding, just for aligning the rows of this matrix of configurations. And also for convenience, we suppose that the tape grows only to the right. So it's infinite only to the right. And on the left, it has a start. This is all for convenience. So this is the first, and the boundary here actually can be computed just as the m multiplied by the polynomial bound. Why? Well, just because the number of steps which we need in order to reach the end of the tape, which is endless, but we use only a finite number of cells inside. This number is bounded by the number of steps which we perform, and this is polynomially bounded. So actually the machine computes on a bounded fixed zone on the tape. So this is the code for configuration. So everything inside this word, we know everything about the situation of the Turing machine. We know the state, and we know where it's located, and we know all the symbols on the tape. Yeah? Is that clear? How do we encode the Turing machine configuration? Okay. And now, or the starting configuration, it starts with some initial state, and we have the input word X on the tape. And then each next configuration is obtained from the previous one using the rules of the Turing machine, which are non-deterministic, of course. So the sequence of configurations of the protocol of the computation can be encoded as a binary matrix. So in each row, you will have the configuration, and you will have this number of rows, which is the size of the length of the computation, the number of steps. So we suppose that if the machine stops before its allowed time, before P of X, we should say that the next configurations will just repeat the last one. So if it reaches the final one, it just can get stuck in it. And also, this is the size, which is the size of the zone of the computation. So again, we have M is the number of bits in every letter, in every byte. And this is the boundary on the memory. It's also polynomial. It's the same polynomial, just because in order to reach the end of the tape, the last cell which is actually used, we have to perform that number of steps. And it's also bounded by P of X. So all the computation is represented by a big matrix, by a protocol of the Turing machine. And it's a binary matrix, so it's just a bunch of Boolean values. And next, what we're going to do next, we introduced this number of Boolean variables, Bij. Each Bij is a specific Boolean variable. There's a big amount of them, but remember, it's polynomial. This protocol has a polynomial size. And next, we construct a formula which says phi x with these variables, B00, B01, etc., which expresses the fact that this matrix represents a correct protocol of a successful execution of the Turing machine on the input X. So how do we construct this formula? Well, I will give only a sketch. The idea is that we should express our condition of correctness of the protocol as a Boolean formula. So the first row should represent the fact that the first row includes this word X and the machine is in the initial state. It is just a series of equivalences. We say that the first bit should be 0, the second bit should be 1, etc. So it's just a concrete configuration. We just express it as just one formula. The third one says that the last row should be in state QF and include the answer yes. So again, this is a concrete constraint on the last row. It just should say that this is 0, this is 1, 1, 0, 0, etc. And the most interesting one, which we will not discuss in detail, is that each next row inside the protocol is obtained from the previous one by one of the rules of the machine. So again, for each line, you have a big disjunction, which says that either this rule was applied or that, or that, or that. And the trick is that this is local. That if you see our configuration, you have to worry only about this part in the middle of it. So you don't think about the whole length. You just take the 3 letters near the head of the Turing machine. And for this, you just implement your commands of the Turing machine. You check that the previous, so you say that the row, I don't know, number I minus 1 includes this, this, and this. And the row I the row I, the next one should include the corresponding result. So this will yield us a huge Boolean formula, but you can easily see that it is polynomial in size with respect to the length of the input, because the matrix is polynomial and the number of clauses which we use is going to be polynomial. So it's going to be a conjunction, but it's not CNF, because in CNF you should have only elementary disjunctions. Here you will have some equivalences and stuff like that. So this is just a Boolean formula. So again, you will have phi of x, which is a Boolean formula of polynomial size, which is obtained from two sources. So the first one is x, which is our parameter. And the second one is the definition of the Turing machine, which is just fixed. So we do not use it in computational estimations because there's a concrete problem A and a concrete non-deterministic Turing machine which solves it. So this is the construction. This is all Boolean formula. And now reduction. So the reducing function takes x and just yields phi of x. It's polynomially computable. And now we say that the result of the run of the Turing machine is 1 if and only if this formula is satisfiable. Exactly. So satisfiability of this problem, of this formula, sorry, means that the Turing machine has a valid computation which yields 1. So it means that a non-deterministic machine has a computational track which yields 1 on x. And this is exactly that a of x equals 1. And we're done. We see that a is reducible to sat by this very reduction. And a was taken arbitrarily from the class NP. Therefore, we get NP hardness of sat. And since sat is an NP itself, that is NP complete problem. So this is the basic theorem of NP completeness. We have sat, which is NP hard. Now, all other things that can be done by backwards reduction. So today we'll show that 3 sat, so sat for 3 CNF, is already NP complete. We will do it by a reduction, by Tseitin transformation. And in the next class, we'll show the same for Hamiltonian part. So NP completeness of 3 sat. So 3 sat is a specific version of sat, where we allow only 3 CNFs, not arbitrary formula, but 3 CNFs. And trivially, it is reducible to sat. Well, here the reduction function is just, actually, it's just identity. You take a 3 CNF, and if you can check satisfiability for arbitrary formulae, you just use that algorithm for 3 CNF and you win. But this is not the reduction we need. So we know that 3 sat is easier than sat, or not harder. But we have to show that it's not easier. We have to show that it is greater or equal. So we have to reduce sat to 3 sat. Instead of trying to satisfy an arbitrary formula, we have to reduce the satisfiability question to satisfiability for 3 CNFs. Yeah. So this should be a reduction like that. So this is done by Tseitin transformation. So again, one more name in this field, Tseitin, who invented the transformation of Boolean formulae to equisatisfiable 3 CNFs. And this equisatisfiability will be of polynomial size. So equisatisfiability means that this new formula is satisfiable if and only if the old formula is satisfiable. So notice that notice that equisatisfiability is weaker than equivalence. So of course, if you have just 2 formulae which are equivalent, just logically equivalent, then they are of course equisatisfiable, because if you satisfy one, you by the same assignment satisfy the other one. But this is not possible for Tseitin's theorem because there are 2 obstacles. The first one is that if you transform your formula into a CNF, then you can get exponential blow up. And you've seen that. If you start transforming, you have to open up all the brackets and your formula could exponentially grow. This is the first problem you can come across. The second one, there exists some formulae which are not 3 CNF. So they can be 4 CNF, but not reducible to 3 CNF equivalent. So therefore, not any formula can be equivalently transformed into 3 CNF, even without the boundaries, but if you need polynomiality, it's impossible. But you can make it equisatisfiable. And we'll show how. So the idea of Tseitin's transformation looks like the translation into a three-address or what they call assembler code. So if in a higher level language, like I don't know, Python, you can write things like that, say complex algebraic expressions, how do you translate them into a machine code? How do you really implement them on the CPU? You cannot pass these directly to the CPU. And as you know from your home assignment, you have to parse this, find out a syntactic tree of the formula. This is not a Boolean formula, it's an algebraic formula. And then what you do, you compute them one by one. So first you compute this, and you keep your result in some new variable, T1. So these are new variables added, therefore it's not equivalent, but it's equisatisfiable. So you take A and B, you add, and you store your result in a new register. This is why it's called three-address code, because there is an address for that, and new address for result. You allocate new memory. Then you do the same here, and then you have these two, and you multiply them. And R is the resulting part. It could be called T3. It's also a new variable. So this is how you usually compile your algebraic computations on a real, say, computer. So Tseitin did the same. I presuppose that maybe he did it before this all was invented, but nevertheless. So Tseitin does the same for Boolean formula. So suppose we have a formula, and for each subformula we introduce a new variable and write a corresponding equivalence. So there is an example. This is a Boolean formula. By the way, is it satisfiable? How do you think? Is there a satisfying assignment for that? Yes. Well, it is a disjunction. So if you want to satisfy it, you have only to satisfy one. And here you have an implication. Again, it's always satisfiable. So it's not P or Q. If you make Q true, you satisfy everything. But just for example, we will rewrite it into an equisatisfiable CNF. Not only CNF, but 3 CNF. How should we do that? Well, this is how it's written. The colors will be useful for us in the future. So for each subformula, we introduce a specific color and specific variable. So this is going to be T1, which is equivalent to P implies Q. P implies R is denoted by T2. T3 is for Q implies T2, so for this one, this subformula. And then T4 is the big disjunction. And finally, we claim that T4 is indeed true, because we want to satisfy an assignment. So in our assignment, we should satisfy the whole formula. So we should make it true. And we claim that this conjunction, well, it's not yet a CNF, but we will transform it into a CNF in a minute. It's easy. This conjunction is equisatisfiable with this formula. Why? Well, if this conjunction is satisfiable, we just take this satisfying assignment and take its, I don't know, sub-assignment for PQR. So we forget about the values for T1, T2, etc. And take this and substitute it here. So what happens? So we have these equivalences. So this means that the value for T1 is the same as the value for P implies Q under this assignment, right? The value for T3 is Q implies T2. So T2 is the same as P implies R. So T3 is going to be the same value as this. This means that T4 should have the same value as the whole formula. And also at T4 should be 1. So this means that under this assignment for PQR, we will get satisfiability. So again, if this big formula is satisfiable, the original formula is also satisfiable. And in the opposite direction, if we manage to satisfy this, we just take we have to find an assignment for T's. How do we satisfy T's? How do we assign them? Well, we take the corresponding subformulae and assign these variables to T's. So this is going to be assigned to T1, this is going to be assigned to T2, this is going to be assigned to T3, and this is going to be assigned to T4. What happens then? The formula is satisfied by this assignment, the original one, so T4 is going to be true. So this is okay. This is satisfied. And each this equivalence is also satisfied, well, just by definition. We took the same variables. So this is the same as this. They could be both 0, they could be both 1, we don't know, but they are the same. So this guy is true. And the same for all others. So if we satisfy this, we satisfy this. So they're equisatisfiable. The satisfying assignments are different because here we had to add satisfying assignments for t's, which were not the case here. Okay? So this is the transformation from a formula into something which is closer to a 3CNF. So exactly here we have a conjunction of formulae in each formula we have three variables, but it is not a disjunction. It's rather an equivalence. And here is T4 with just one. Okay. And now we transform it into 3CNF just equivalently. So there's no more adding new variables or equisatisfiability tricks. It's just equivalence. It's done by the following table. So we suppose we want to say that Tk is equivalent to T1 and Ti and Tj. What does this mean? That should be implication from Tk here and from this here. So what does it mean that, okay, for disjunction, for example. So it's not Tk implies Ti or Tj. It's written like that. It's not Tk or Ti or Tj, right? And the opposite implication says the following. It says that Ti or Tj implies Tk. And this means that both Ti implies Tk and Tj implies Tk, right? And this is written as follows, not Ti or Tk, not Tj or Tk. So dually for conjunction, you can just, well, if you are in doubt, you can just check these equivalences just by truth tables. You can implement it on a computer, for example. For implication, you have basically the same, because it's just a disjunction actually. And negation says like that, how do you say that they are negated? That at least one of them is 1 and at least one of them is 0. This means that they could not be both zeros and not be both 1. So they should be opposite. So if you have more Boolean connectives, I don't know, you have equivalence, if you have something else, you can also write down the corresponding thing. And these are 3CNF clauses. They include either 3 or 2 literals. So translated into 3CNF. You couldn't do this with 2CNF. Why? Because polynomial is decidable and SAT itself is NP-hard. But for 3CNF, this is doable. So in our example, we get the following. Well, I hope there are no typos here. We can check, for example, the first one. T should be equivalent to P and implies Q, T1. So it says T1, this row here. Yep, it should be not P or Q or not T1. Should be P or T1 and not Q or T1. Yep. So this is exactly here. We have 3 clauses instead of 1, but it's a good 3CNF. And all these transformations are polynomial, of course, right? Next, we have the blue, the green, and the brown one here. And T4, which is just a clause with 1 literal. So what we have now, for each Boolean formula, we polynomially compute a 3CNF, which is equisatisfiable with the original one. And as you can now easily understand, this is exactly the required M reduction. So we started with we started with a Boolean formula. We transformed it into a 3CNF. And now to check the satisfiability of the original formula, you apply this transformation and check the satisfiability of the 3CNF. This is a reduction of the general SAT to 3SAT. And the theorem is that 3SAT is NP-hard. And of course, it is in NP because it's easier than SAT. So we now have 2 NP-hard problems, NP-complete problems, SAT and 3SAT. So 3SAT is a special case of SAT, but actually it's equivalent to SAT, polynomially, mutually reducible. So, well, this is the core of NP-completeness theory, as it is the theory of the complexity theory on the condition that P is not equal to NP. Next time we'll discuss Hamiltonian path and also show a reduction. So we take Hamiltonian path just to show a non-trivial reduction. Also in your exercises, you will have 3 coloring problem, which is mutually reducible with 3SAT. Just this is for you to understand how these reductions work. In computer science, the status of these problems is quite interesting. So the usual job of, well, not a computer scientist, but actually a programmer or an algorithm designer, is to design algorithms, which means that this guy shows positive things. That by constructing a concrete, efficient algorithm, we prove that a problem is solvable, and it is solvable in reasonable time, say polynomial, or even better, something like n squared or something like that. This is the usual workflow of algorithm design. This is, say, positive computer science. So proving NP-completeness is negative computer science. It's showing that some problems are hard and you should not try to solve them. So if you, before hiring a programmer to implement an algorithm for a problem, or an algorithm designer, you should ask a computer scientist whether this problem is not hard from theoretical consideration. If it is NP hard, if it's NP complete, you better not try to solve it in polynomial time, but try to find a workaround. Which workaround? Well, try to find some specific case of the problem which is solvable easily or something like that. So if your problem is harder than 3-sat, if you can reduce 3-sat to your problem, then you should not try to implement it. It will not be polynomially solvable unless p equals np. So the theory is conditional here. Well, as for these problems, will, as I said already, we'll have Hamiltonian path, we'll have also recoloring, we'll have these problems in Boolean formulae. The idea is to develop some intuition on which problems are polynomially solvable and which are not. So ideally, people who know much in these fields of computer science, they should have some intuition in their mind which problems can be solvable polynomially, which can be hard. So if it is polynomially solvable, then you have to implement an algorithm. If it's supposed to be NP hard, you should implement the NP hardness proof. So returning to our picture, you can ask what is here in between. Well, the answer is as follows. I will not prove it and even will not show the examples, but just for you to understand the picture, in the presupposition that P is not equal to NP, as I said, otherwise everything trivializes, the situation is as follows. You have P, you have NP complete problems. Of course, these guys do not intersect, because if there exists at least one NP complete problem which is solvable in polynomial time, then P just equals NP, as we know. But there are also intermediate problems. So I think this is proved by Ladner or someone like that. So there is a theorem that if P is not equal to NP, that there exist problems strictly in between. Unfortunately, for these problems, I think there is no good reduction theory, because you have to do two reductions. You have to make it easier than NP and harder than P. And most examples of these problems are artificial, but there are some problems which are highly supposed to be intermediate. And one of these problems is graph isomorphism. So it's quite natural problem. You have two graphs, and the question is whether they're isomorphic. So whether you can map one graph onto another, onto the other, and they will just map one to one, edge on edge. So this is the isomorphism of graphs. Of course, it's NP, because if you guess the isomorphism, guess this mapping, you will check it polynomially, linearly actually. But the problem whether two graphs are, or not linear, quadratically, whether two graphs are isomorphic, it's NP. We don't know a polynomial solution, and we don't know a proof of NP completeness. So this is a good candidate for an intermediate problem. But as I said, this is, as far as I know, not proved yet, even under the conjecture of P not equal NP, of course. But there are artificial examples in here. So there is a hierarchy of problems in between. But these are some sort of exotic examples. So most problems are either P or NP complete inside NP. So this is a dichotomy. But really, they could be intermediate ones. So now yeah, I think we will finish this lecture a bit earlier because there's a big amount of material today. So it's maybe the hardest lecture in the course. But before finishing, I would like to show something beyond decision problems. So there was a question in maybe here, maybe in the practical class, I don't remember, that okay, we're talking about NP. NP is only for decision problems, and P is also only for decision problems. But what about problems which should yield something more? So for example, we have the Hamiltonian path problem. So as we formulated, it's an existential question, whether there exists a Hamiltonian path. But of course, the thing which people would usually wish to see is, if you have the Hamiltonian path, then we'll show it, present the Hamiltonian path. And also, you could ask something else. You can say, well, maybe you should yield all the Hamiltonian paths in the graph, or all satisfying assignment. Or maybe you have to count them, or something else. So beyond decision problems, so an NP decision problem that says that whether there exists a witness Y or a hint Y such that, or there exists a computation path which yields 1, there could be, so for example, satisfying assignment is a good witness. It says that the formula is satisfiable. There is a search problem, which says that if a witness exists, then please give it to me, please yield it. So the search problem gives the answer of not only yes or no, it can either say no, there is no satisfying assignment. Well, let's use this as a running example. When I say satisfying assignment, you can think about a Hamiltonian cycle or color-Renova graph or something like that, isomorphism. So if you answer no, you just answer no. But if you answer yes, you should present at least one satisfying assignment. This is a search problem. Of course, the search problem is at least as hard as the decision one. Because if you can solve the search problem, you can just, instead of yielding the witness, just say yes. So it's not easier, but we'll say it's actually not hard. So there is a counting problem. It's called sharp P. This hash is called sharp, just as in music, they have sharp and flat. So we are asking for the number of witnesses. For example, the number of satisfying assignments. So instead of saying that we have we can say, okay, the satisfying assignment exists. We can say that, okay, the satisfying assignment exists, and this is one example, but we're asking for the number of them. There could be only one, but there could be a big amount of them. We're interested in how many assignments. For example, maybe the assignment is quite rare, or maybe most of the assignments are satisfying ones. So this is the counting problem. And finally, we could ask for all witnesses. So for example, we could ask for the user to say, please yield me all the satisfying assignments for this formula, or yield me all the cycles which are good, say Euler cycles or something like that. So the problem of yielding all the witnesses could be unconditionally non-polynomial. We don't need even P not equal NP here. Why? Well, because the answer could be exponential. Just say you could have a formula which is always true. Any assignment is satisfying this formula. And the number of assignments is 2 to the power of n. So here you have no chance to be polynomial just because the yielding of the answer could be exponential. This could happen for polynomially solvable decision problems. For example, you have the problem of solving 2CNF. So satisfiability for 2CNF is done by resolution, and it's polynomial, right? But a 2CNF could have a great amount of satisfying assignments. Say it's P or Q and R or T, etc. So from each clause, you can just take one arbitrarily. It's exponential grow. And if you want to yield all of them, you cannot do this just because there is an exponential answer. What can we do? And we'll discuss this in the end of the course. We can do this, what they call algorithm of polynomial delay. So an algorithm of polynomial delay does the following. It yields all the answers, all the witnesses, all the assignments, say. It cannot do it in polynomial time, but it has to do it as follows. So it starts working. In polynomial time, it should yield one answer. Then it continues working. Again, a polynomial delta of time yields the second one, etc. So why is this polynomial delay useful? Well, the standard example is, I don't know, Google or Yandex, which is the search engine. So the searching problem says that you have an index of web pages on the web, you have to yield the answer which, in a sense, satisfies the request of the user. So, of course, it's all not that rigor as in the satisfying for Boolean formulae. It includes some measure of relevance and stuff like that, but we can say that it is satisfaction of the user's needs in a sense. Of course, the real answer is huge. If you ask something from the search engine could find you an enormous non-polynomial number of possible answers. But how does it really work? It yields you, say, 10 best ones. What does it mean best? We'll not discuss, just 10 some. You look at them. If you don't like them, you ask for the next 10. So you interactively work with this algorithm, and it works fast. And it's a bad idea to generate all the answers and then yield the first 10. This will make the system work very slow. So therefore, it's an online system. Maybe you will get satisfied with the first results of the query. If not, you will ask for next and next and next. The same can be implemented for, I don't know, for 2CNF, for example. So if P equals NP, then any search problem, just searching for one, is, of course, solvable in polynomial time. So we can reduce the search problem to the decision problem. So on an example of the Boolean formula, suppose we know how to check satisfiability. How do we check, how do we find a satisfying assignment? Well, first we check for satisfiability. If the answer is no, we say, no, there is no assignment. Then we try to understand what is the value for P1. What could be the value for P1? We substitute 0 and substitute 1. After we have substituted 0, we check for satisfiability. If it is satisfiable, we just say that P1 is going to be 0. If it is not satisfiable, then since we know that the formula phi was satisfiable, this means that this should be satisfiable, right? Because P1 should be either 0 or 1. It could not be 0, it should be 1. We say that P1 is 1. We have reduced the number of variables and we proceed by induction. So now we check P2, P3, and we yield one satisfying assignment, but not all of them, because they could be both satisfiable, but if we took P1 equals 0, we forget about that. So here we actually run our satisfying checking algorithm n+1 times for the whole formula phi, and then for each substitution. So if P equals NP, then SAT is polynomial time decidable. And if SAT is polytime decidable, then we yield polynomial algorithm for such problem. So this means that polynomiality for decision problems, which is easily more, say, tractable from the theoretical point of view, is the same as polynomiality for search problem. Well, I did this on the example of SAT, but it's the same for any NP problem, just due to Cook-Levin. Any other problem can be reduced to SAT, and this reduction will also keep the witnesses. If you check this, it will make the same. This gives us a polytime algorithm for the 2CNF problem, by the way, for the search problem for 2CNF. Because if our phi is a 2CNF, then we indeed have this algorithm of resolution, which is indeed polynomial, and we can perform this dichotomy. And if we perform these substitutions, then a 2CNF keeps being 2CNF. It will not get bigger clauses. When we substitute zeros and ones, then just if we substitute a 0 instead of a literal, then just we remove the literal. If we substitute a 1, we just remove the clause. The counting problem, on the opposite, could be harder than the decision one. And the example, this is, by the way, an exercise for you. It is DNF SAT. So for DNF SAT, we have the following two statements. First, the DNF SAT as a decision problem is polynomially decidable, right? Because for DNF, we discussed that. It's sufficient just to check each clause. But counting problem, so given a DNF, what is the number of satisfying assignments? If P is not NP, then it is not polynomially solvable. And we'll discuss it next time, or maybe in the lecture after the next. So this is the DNF SAT. So this is about all of the theoretical material for today. So thank you for attention. and I will advertise the home assignments which you will have. So tonight I will post the written home assignment, which you will have to submit, I think, again in 2 weeks. This is the theoretical assignment. Well, the problems there will be mostly on Boolean logic and maybe a bit on graphs, which will be just in the same style as you had on the seminar classes. So nothing, no surprises as usual. And there will be a deadline, and you could submit it either in written form here in class or by email, just a scan of photo or something like that. This will be the second home assignment. And next time we'll discuss the Hamiltonian cycle problem at NP-hardness. So today in the seminar, we'll have the Euler cycle. Just as an exercise, we'll discuss how to solve it. And we will have also on the next theoretical lecture, we'll have an introduction to a framework in Python, which is called Network X, for implementing graphs. And we'll have the third home assignment, which will be a small exercise in a Network X. It will be really small, just for a week. So this is the third one. And tonight I will also publish on the webpage the formulae for computing the final marks. So there will 3 home tasks. These will form what they call the cumulative grade for your activities during the course. And there will be also the final exam, which will be just a written exam. By the way, I discussed it with the study office, and the written exam will be, in a sense, take home. So in order to put all the people into equal conditions, so the people which are now on Zoom, they will, of course, be take this at home and just send me the results. The same will happen for you, which are now in Moscow. So we will not gather you here, but rather, say, in the morning, we'll publish the problems and also send it to you by this general group email. And in the at some point, there will be a deadline. It will be that same day, so it will be really as an exam. So you will have several hours to solve it, and you will have to return it to me either by email or maybe by Google Form. So this will be just for you to for me to gather the results, and I will compute them, and there will be an opportunity for you to see your results before they will be officially put in the metrical and sent to the study office. So this is about the end of the module and the marks. So thank you for your attention, and see you next time.
Первая домашка. Там какой был дедлайн? На сайте написано. Да, 11.